It is 4 in the morning at the Green Bank Observatory in West Virginia. The 700-ton steerable radio dish is locked onto the millisecond pulsar PSR J0740 plus 6620. The recorded waveform shows a perfect periodic pulse, arriving every 2.886 milliseconds, with timing precision better than 1 microsecond. And the source is a spinning neutron star roughly 4,000 light-years away. Tonight, we cover the neutron star. Joining me are a theoretical astrophysicist and a pulsar observational astronomer.
A neutron star is the collapsed core of a massive star at the end of its life. When a star between 8 and 25 solar masses exhausts its nuclear fuel, the core collapses in less than 1 second. Gravity forces electrons and protons together into neutrons plus neutrinos. The collapse halts when neutron degeneracy pressure becomes strong enough to support the weight against gravity. The result is an object of 1.4 to 2.3 solar masses crammed into a sphere only 20 to 25 kilometers across. The theoretical prediction came in 1934.
The first observational confirmation came in 1967 at Cambridge. A young graduate student noticed a faint periodic radio signal pulsing every 1.337 seconds in routine radio survey observations. The signal was so perfectly regular, it was initially nicknamed LGM-1 for Little Green Men. After ruling out artificial origin, the discovery was published as the first pulsar, PSR B1919 plus 21. Her thesis advisor, the 1974 Nobel Prize in Physics for the discovery. She did not.
The internal structure has at least 4 distinct layers. The atmosphere is a 1 centimeter thick plasma of hydrogen, helium, and iron. The outer crust, 300 meters thick, is a crystal lattice of heavy ions in a sea of degenerate electrons. The inner crust, 1 kilometer thick, contains nuclei plus free superfluid neutrons. The outer core, 10 kilometers thick, is superfluid neutrons plus protons plus electrons. The inner core is still unknown. It may contain free quark matter, hyperons, kaon condensates, or a mixture. Central density reaches 10 to the 18 kilograms per cubic meter.
Neutron stars are observable because they are rotating magnetic dipoles. The surface magnetic field strength runs from 100 million Tesla in ordinary pulsars to 100,000 billion Tesla in magnetars, over 100 trillion times the Earth's field. As the star rotates, the magnetic dipole sweeps a beam of radio and X-ray emission across the sky like a lighthouse. Rotation periods run from 1 millisecond to 10 seconds. Millisecond pulsars were spun up by accreting matter from a binary companion to spin rates of up to 700 revolutions per second.
The maximum possible of a neutron star is set by general relativity and the equation of state of nuclear matter at densities above nuclear saturation. The Tolman-Oppenheimer-Volkoff equation gives this limit between 2.3 and 3 solar masses depending on the assumed equation of state. Beyond the limit, the star collapses to a black hole. The heaviest measured neutron star is PSR J0740 plus 6620 at 2.08 solar masses. These mass measurements are now the principal observational constraint on dense nuclear matter physics.
On August 17, 2017, LIGO detected gravitational waves from the merger of 2 neutron stars, 130 million light-years away. 2 seconds after the wave signal, a gamma-ray burst was observed by the Fermi satellite. Within hours, follow-up telescopes spotted the optical kilonova. The event GW170817 was the first detected neutron star merger and the first multi-messenger astronomy observation. The kilonova produced an estimated 10 Earth masses of gold and platinum through rapid neutron capture nucleosynthesis.
Modern observatories use neutron stars as natural laboratories for fundamental physics. The Neutron Star Interior Composition Explorer, or NICER, on the International Space Station measures X-ray emission profiles to constrain the radius to 1% precision. The North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, uses arrays of millisecond pulsars across the galaxy as an enormous galaxy-scale interferometer to detect nanohertz frequency gravitational waves. In 2023, Nanograph reported the first evidence of a stochastic gravitational wave background.
3 takeaways. First, a neutron star is the collapsed core of a massive star. Predicted 1934. Mass 1.4 to 2.3 solar masses. Radius 20 to 25 kilometers. Density 10 to the 18 kilograms per cubic meter. Second, the first pulsar was discovered 1967 at Cambridge. Magnetic fields up to 100,000 billion Tesla. Rotation 1 millisecond to 10 seconds. Third, GW170817 in 2017 was the first neutron star merger detected. Kilonova produced gold and platinum. Thank you, theorist. Thank you, observer.